Вы очень хорошо выглядите.
Вот.
Спасибо
Ну,
большое.
ну что ж, давайте начнем. У нас сегодня выступает Anar Dosi из Харбина. Доклад называется «Некоммутативные локализации и совместные спектры, сжимающие квантовые плоскости». Вот. Today our speaker is Anar Dosi from Harbin Engineering University, and the title of his talk is "Noncommutative localizations and joint spectra of a contractive quantum plane." Please.
Мока.
Yeah, okay.
Не
Yeah,
слабо.
thank you. Yeah, is it visible now? So let me
Yeah.
just enlarge it. What about now? Is that okay?
Yeah, good.
Ага.
Yeah, it looks better, right?
Mhm.
Okay, okay. Yeah, okay, yeah, thanks for the invitation. Just be aware, please, we may have experience with the internet drops. Today happened twice. I don't know why, but I will be back in a few minutes. Yeah, sorry for that. Okay, yeah, let me start. So first, I will just explain what does localization mean, and thereafter I will switch to some historical moments and motivational stuff. But first, let me say what is that? So first of all, localization is a purely topological homology concept. So just briefly review what it's all about. So our main category will be a category of Fréchet spaces. So all underlying vector space, they are Fréchet spaces. So suppose we have a Fréchet algebra, left Fréchet module. So as we know, what has been free module, right? Free left module, if it can be written like a projective tensor product of A and some Fréchet space. And equipped with the natural left action, right? Left A action. So retracting the category of left modules of a free module is called projective module, as we know, projective left module. So just a module summoned of a free module. So by projective resolution of a left module, we mean a chain complex of left projective A modules with a connecting morphism pi. Yeah, so that this stuff, this complex is admissible. That means splits as a complex of Fréchet spaces. So that's, in this case, we say that we have a projective resolution in topological homology. Okay. So now suppose we have another algebra, Fréchet algebra. It can be even polynomial. So suppose we have some functor, additive functor. Then by Fn, respect f at the upper index n. So we use the denote as derived functor of f. So that means, so we need to apply the functor to my resolution, P, right, for a projective resolution, and then calculate the homology or cohomology groups. Well, since all projective resolutions are homotopy equivalent, so actually, whatever written here, f and x, does not depend on particular choice of my resolution, projective resolution. So if, for example, we have this functor tensoring from the left over home, then we used to write torsion group NAX or X. So there's a standard homology cohomology groups. And also a notation like transversality property of two modules, left module, right module, if all homology groups, they are vanishing for all n more than or equals 0. It's also a notation introduced by Taylor. Okay, that's some elementary stuff from topological homology. Okay, what has been localization? So now suppose we have some base algebra B and connected to Fréchet algebra A, so with some continuous algebra homomorphism. Well, so B can be like in the pure algebra. In this case, we say that I mean, we assume that it's cubed with the finest local Connell's topology. Okay, so we can introduce purely in the concept of topological homology concept. So we can say that B is a polynomial algebra, and we have a connecting morphism to our Fréchet algebra. So as you know, every morphism actually introduced the morphism of groups of homology. Whenever M, say, is a Fréchet bimodule. If you take any bimodule, so there are canonical morphisms between groups of homology. So if all these connections, they are isomorphisms in algebraic sense, so that means this map implements isomorphism of the homology groups for every Fréchet bimodule. Then we say that this morphism is a localization. So localization, in some sense, identifies, I mean, homology functors over B and over A. Over B's can be quite a pure algebraic stuff, but over A's can be from, I mean, over A is topological homology stuff. Anyway, if this map implements an isomorphism of groups of homology, then we say we come up with a localization. Yeah, for example, we can take, instead of M, like free bimodule like that, and then calculate in the both sides, we can see that these map tensoring over B's and topological isomorphism, and all torsion groups AA, they just vanishing, or for n positive. So in this case, A is considered to be a B bimodule through this homomorphism I. So that's proper definition for localization. Well, so now some details, what we can do here. For example, we can take some bimodule resolution of B. Say admissible projective bimodule resolution of B. Again, it's going to be quite a pure algebra B and just standard algebraic resolution. And then apply the functor tensoring from the both sides of a B to P. And we can get a new complex which can be augmented by method of multiplication map. As a result, we come up with this sort of complex A and connecting, I mean, tensoring A from left and right to our P. Well, if this one, whatever we got, is admissible, as I told you, the splits as a complex of Fréchet spaces, then certainly this map is a localization. So look, we got our bimodule resolution for A by means of P for B. So, but this is a bit stronger. In this case, we say that is an absolute localization, or it comes from terminology from algebra, like stably flat over B. And certainly in this case, we have identification of groups of homology for every bimodule, even not necessarily for a Fréchet one, for any bimodule. Well, but there is one more moment. So we can assume that A and whatever we got here, suppose they are all nuclear Fréchet spaces. Sometimes you will see examples like that. Then actually this map is a localization. This is a result due to Taylor about 1972, when just this complex is exact, not necessarily admissible. So again, let's take resolution, apply the functor, we got this complex. Suppose it's just exact, not necessarily splits, I mean, just exact, and all stuff, they are nuclear spaces, nuclear Fréchet spaces. Then this is a localization. So that means you can compute the homology groups based on this resolution. I mean, still it allows in this category to calculate all homology groups, and you will see this sort of identification with B and A. Yeah, again, this one happens if A and all the stuff they consist of nuclear Fréchet spaces. Then still you can do the same calculations. Okay, that's the difference in some sense, absolute and non-absolute. There's localizations. So now motivational stuff, why we need this stuff. We are tackling with the non-commutative complex analytic geometry. So for us, B stands for non-commutative variables. It's a base algebra of non-commutative variables. But when we are localizing it, Fréchet algebra localizations, they actually represent some algebras of local sections of germs of non-commutative holomorphic functions in B. So in some sense, this property, this purely homological property, actually provides us some local algebras. Local in this sense, like in small neighborhoods. And thereafter, we can glue them up to generate the structure sheaf. So structure sheaf where? Certainly we in the parallel manner we should generate non-commutative space like spectrum. So this is a topological space. They are actually as a set of all reducible Banach space representations of B. Certainly it should be equipped with a special topology. They used to be non-Hausdorff in general, but it can be Hausdorff as well. So over this topological space, I need to generate my structure sheaf, non-commutative structure sheaf. So that structure sheaf locally, they are generated by means of localizations of B, and thereafter we need to glue them up to generate the structure sheaf. So this couple exactly stands for our non-commutative complex analytic geometry of B. Certainly, next step, what about non-commutative O functional calculus problem for the Banach space representations of B? And this theory, in turn, associated with the spectral theory, non-commutative B spectral theory, and related topics. So overall, this is just sort of motivational stuff for why we are doing this. Why we are developing this theory. So what is non-commutative complex analytic geometry? So spectrum, structure sheaf, functional calculus problem, and also the joint B spectral theory. This is quite a rich direction. Well, for example, if base algebra is just polynomials and their localizations, they actually, the Fréchet algebras of holomorphic functions on domain of holomorphic, for example, over polar disks, over local stuff, all of them, they are localizations. So locally, we have these algebras. They can glue up to a sheaf. So we come up with the standard complex analytic geometry, right? So, and related holomorphic functional calculus problem, mainly developed by Taylor and related spectral theory, say in his famous paper 1972, a general framework. Okay. Well, what about non-commutative case? Certainly some historical moments here. So what happened in non-commutative? There was some development in this theory in the non-commutative case. For example, the case of a universal enveloping algebra for a fine-dimensional Lie algebra. Yeah, this problem. So what about localizations of this algebra? is gradually developed in the last maybe 20 years, mainly by Aristov, Perkovsky, and by me in a series of papers. Certainly, the first target was what about canonical mapping to its Arens-Michael envelope, like algebra of non-commutative entire functions and variables of G. Well, even in this case, there were problems. So certainly, for example, this is a localization when G is abelian Lie algebra, and that's not the case when G is a semi-simple Lie algebra. Yeah, this one actually proved by Taylor himself in the 1772, again in his papers, 2 or 3 papers mainly. Well, 2006, Perkovsky proved that solvability of G is a necessary condition for this map to be a localization. So the ideal case was a nilpotent one, right? In nilpotent case, I did some investigations in some my papers, but my motivation was mainly developing the implementation of Taylor's framework in the non-commutative case. But certainly independently, the localization problem investigated by Perkovsky, by Fréchet, within some papers, and they completed by Aristov recently 2020, where it was shown that this map is a localization for every nilpotent Lie algebra. Well, but what about solvable Lie algebra case? The case of non-nilpotent but solvable Lie algebra recently solved by Oleg Aristov. As far as I remember, he had a talk in our seminar concerning this problem. So what's the result? So all Q is a stably flat over universal enveloping algebra if and only if G is a solvable Lie algebra. Well, but for other algebras, like for example, like for the structure sheaf, so it's so-called formally radical functions. It was also done by me in the 2010. So in the case of a nilpotent Lie algebra, so we can construct, so we can solve the problem completely. We can generate the structure sheaf, functional calculus problem, but in some formal level. That's why it's called the formal radical functions here. Okay, that was some historical moments. Now let me switch to my task. So what I'm going to do in this presentation. So again, I had several talks concerning the quantum plane. I will continue this development here. Again, we know what is a quantum plane. It's algebra generated by 2 variables with this sort of relation. So again, it's Arens-Michael algebra. Arens-Michael envelope is denoted by OQCXY. So again, they can be treated like entire functions. It generates x and y. Okay, so we have a description for this Arens-Michael envelope. They consist of convergent power series like that. If Q less than or equal 1, again, that's a result due to Alexei Perkovsky, 2008. So we can calculate all continuous characters. So, one-dimensional reducible representations. It turns out that the space of all continuous characters can be written like a union of 2 complex lines. They can be embedded in the C2 like x-axis and y-axis. Okay, that's my continuous characters. Well, the case Q more than 1, Q less than 1, they are the same, so they can be reduced to each other. So, but when Q equals 1, this is quite different theory. So if Q is not 1, so we have nice property here, like Arens-Michael envelope is commutative modulates Jacobson radical. So that exactly means like all reducible Banach space representations, they're just one-dimensional. So in this case, spectrum just consists of characters, the continuous characters. And we now answer is union of two complex planes. Yeah, again, that's the case when Q is not 1. So that's why it's for us important, the contractive quantum plane. Well, we have a nice result, again, proven by Alexei Pyrkovsky. So this map is an absolute localization. So actually, we can draw some algebraic localization to this stuff, to topological homology. So we come up with the following free bimodular resolution. It looks like that. So we are translating itself, adding up, and the same algebra translating itself. Look at the differentials. They are standard in terms of right multiplication, left multiplication operators by y, by x, the same by x, by y. Look left and right. So what's the result? If we connect this one as a multiplication morphism to our algebra, this turns out to be a admissible complex of these modules, right? So it's just a nice resolution. So this embedding is an absolute localization. Okay, next step. Now suppose we have another algebra, Fréchet OQCX algebra. So that means suppose we have a new Fréchet algebra with a connecting morphism. I wish to draw the localization property to A. So as I told you, I'm going to apply this functor to my resolution. Then we come up with a very similar resolution with the same differentials. Just instead of my Arens-Michael envelope, we have just algebra A itself. And also it can be augmented by means of multiplication morphism. So look, we come up this sort of complex of free A bimodules, right? Okay. So this one is an absolute localization if this complex admissible, in particular exact. And in this case, this one provides a new A bimodular resolution for the algebra A. But again, there is a moment. If A is a nuclear Fréchet space, if A is nuclear, then all stuff is nuclear. And then exactness will be enough for us. If it's exact, then again, this is a localization, but not absolute, but just localization. Or this embedding is a localization. They are the same in this case. So that means I can compute all my homology functors just based on the quantum plane itself, right? Yeah, there's a moment here. So this is a localization if and only if this is a localization. They are the same. Because embedding of the quantum plane to Arens-Michael envelope is a localization. So that's why here they're equivalent. Okay, so the moment is that, so if A is nuclear, then we need just to prove exactness of this complex. And then we can compute all the homology functors, or homology groups, how it's better to say. Okay, so the potential candidates for localizing algebras. What might be our algebra A? Oh, look, we have 4 candidates for them. So actually, I told about all of them in my previous talks, but I will briefly recall again. So what they are. So this stuff, holomorphic functions over x-axis, formal over y-axis. This is a formal behavior over x-axis, holomorphic behavior over y-axis. This is the most important one. I mean, connecting both at 0. This is sort of algebra which stands for 0. I will explain what is that. So all stalks, they are meeting each other at this inside of this algebra. Anyway, this is our sort of algebras that comes out non-commutative complex analytic geometry for in the formal lever for the quantum plane. For contractive quantum plane of this free one, but this is for any Q. This is applicable for any Q. Yeah, but the nice property that all of them, they are nuclear Fréchet spaces. So for localization, I need just to prove the exactness of the previous complex, as I told you. Okay, now let me start with the easiest one, with the formal power series. And thereafter, I will switch to other one, and that will be easier to catch up what's going on here. Okay, let's start. So this is a formal power series in generators X and Y. Okay, so, but I can equip with a special multiplication so that the canonical map that variables X and Y, they are mapping to X and Y here. They represent the variables of quantum plane. So the multiplications are following. If you have two formal power series, but let's keep the order, first X, then Y. If you multiply them, look, we have this sort of multiplication which involves the Q. So actually you can prove that this is an associative multiplication. As a result, it's an Arens-Michael-Fréchet algebra. Well, to have a better understanding of this multiplication, I will do the following. Let's say the Q multiplication. So we can do like that. We can write down as a left formal series. I mean, the formal power series over Cx, or leaving X here, formal power series over Y. Anyway, you know, right? What is that? So we can do like that. F can be written like f of x's and powers of y, or all the powers of x and g of y, right? Formal power series. So if you multiply them like in the first case, like cxy, it looks like that. Look, you're getting this. This is just formal power series of one variable. This another one, just plug in q power y, multiply them. This is a standard multiplication. And as a result, we have the power series, all right? So this is from left-hand side. Or you can do from the right-hand side. Look, now f and g, the formal series over y. And look again, we have the powers of x. So the both, there are multiplications that's extending the original multiplication of the quantum plane, our algebra. Yeah, but look at here. We can do the following. In the first formula, we can replace C of x by algebras of holomorphic functions on some Q open set. So what is mean Q open set? So it's a standard open set in the complex plane, but if you multiply it by Q ux, it will be inside of ux. So it's stable under all Q contractions, like whenever you're multiplying, all should be inside. Yeah, look at here. So if x from ux, Q powers also should be from my open set. So that's why I need this condition like is Q upon set. But certainly in this case, you should assume that Q less than 1. So just contraction here. So it makes sense, this makes sense, the multiplication of two holomorphic functions makes sense, sum makes sense. And as a result, we come up with the power series. So this is the meaning of this algebra, or ux, y. Or you can do in opposite way. You can do the same for uy. Again, q upon set on the y-axis. And the same is here. This multiplication makes sense, sum makes sense. So we have a power series in terms of x. So in the case when q less than 1, so we can also generate these two algebras. Again, they are all Arens-Michael-Fréchet algebras. So we introduce the free algebras. Yeah, let's say about these formulas again. So whatever you have in terms of x, if you wish, move y from the left to the right, q power n turns up here. If you wish, move x from the right to the left, q power n pops up here. Yeah, that's true for all, formal power series or holomorphic functions, whatever we have. Okay, about this first algebra, CQX, this has the continuous trivial character, 0, 0. It's just annihilating both variables, x and y. And this one is actually only continuous character, nothing else. So spectrum just consists of 0, 0, and 0, 0 actually represents the points from my character space. I told you we have two lines that crossing the x-axis, y-axis. So 0, 0 stands for the spectrum of this algebra. So this algebra is actually local. Radical consists of the kernel. So it's quite simple algebra. So local algebra with only one unique closed two-side ideal generated by x and y. Okay. Well, let's try to do the same. The calculations of our complex. Do you remember I told you about this complex? I wish to generate I wish to have the bimodal resolution here. So if you plug in here, we need to take the two copies of it and tensoring it. Well, once you're tensoring, you can leave y2 always on the right. Look, you can do it everywhere. Look, this is our complex. You can do y2 always on the right. And this is our complex. And here we can easily calculate all differentials and multiplication morphism with respect to y2. Let me say like that. So what I want to say, let me explain. So look, differentials, they look like that. They are actually lower triangular matrices. On the diagonal, we have something simple stuff generated by means of multiplications. On the diagonal, we have some differential operators. Anyway, we don't need. And surprisingly, the multiplication morphism also looks like that, like a lower triangular. So we have a nice complex with the lower triangular stuff. And it's diagonal, whatever left on the diagonal. Actually, it's also complex. We can precisely compute it. What is that? The so-called left diagonal formal Q complex. And it's actually exact. So it's actually exact. And the same idea applicable to both algebras. Holomorphic cases. So what's conclusion? Embedding is a localization for every Q. And Bose embeddings, in the holomorphic case, whenever Q less than 1, they're also localizations. Whenever U, Ux, Uy, Bose are Q open subsets. So this result is relatively easy. I mean, we can directly calculate differentials, detect the lower triangular shapes, calculate the diagonals, and we can prove that diagonals, they are exact. And look, that's a result. Well, the proof is based on certainly on the following general result. Let me say about few mentions here. Suppose we have free spaces, they are direct product of the Fréchet spaces, and we have a continuous linear operator or map from X to Y. And as you know, as in the linear algebra, every continuous linear operator can be given by means of a matrix, infinite matrix. So we say that there's a triangular operator if its matrix is triangular, right? Say lower triangular. Okay, so it's built up by means of SMN. So by triangular cochain, we mean this sort of complex. Well, TS is what? And Bose operators are, they are lower triangular. Well, in this case, automatically we have their diagonals. Look, that's their diagonals, XM, YM, ZM, SMM, TMM. They also, I mean, the cochains, the multiplication is 0. Okay, so that's called triangular cochain. Yeah, look at this lemma. So if all diagonals, they are exact, then so is original complex. Well, but if, for example, diagonal operators, they are topological injective maps, then so is the X, I mean, so is operator S. Yeah, this is a nice lemma. I used it a bit earlier, about 15 years ago, and recently Aristov started to use it in probably several times. So especially this part, topological injective maps, that belongs to Aristov. So that's why I joined them, called them Aristov Dosi lemma. Yeah, and Oleg has a special joke about this lemma, but it's very rational. Anyway, this is quite a nice technical lemma. You can use it, and it's quite general and simple, and the proof is not so hard. Yeah, but pay attention, the reverse is not true. So the exactness of a triangular cochain, it doesn't mean that it should be, the diagonals must be exact. So this one's shooting in one direction, so not in opposite. And you will see below example of this case of the Fréchet algebra. It has also somewhere like triangular shapes and is actually exact, but diagonals, they admit some homology groups. Okay, so opposite is not true. So this is a lemma. Okay. So now let's switch to main algebra, as I promised, the last algebra. So algebra is a structure sheaf of the formal geometry of this quantum plane. So what is that? We're going to pick up these two algebras, as I told you, left and right, both, and actually there are quite a canonical morphism to formal power series. So what is that? So you can take the coefficients here, which are holomorphic functions, and just expand them as a Taylor series, and then unify with y, and you will end up with the formal power series of x and y. And the same is here. So what is that? It's just so-called fibrate product of two algebras. So we need to pick up all couples which are compatible here. So this generates a new algebra, FQU. Because again, Arens-Michael-Fréchet algebras, Fréchet algebra. So, well, I had a talk about this algebra, so I told this the result, but let me mention it again. So this algebra has a nice description. First of all, standard algebra for homomorphic functions over U, but be aware, U again, it has two components, Ux, Uy, so Q open set. So this one can be embedded in here as a subspace, and it can be decomposed like that. Characters, they are reduced to U, so sort of one-dimensional variety, so this is quite natural. But the most important part, this algebra or sheaf can be obtained by means of the structure sheaf as a quantization. Look, we should quantize it, original structure sheaf, in a special way. And as a result, we can end up with FQ, but as a Fréchet space, not as an algebra, certainly. So this Fréchet space structure looks like that. I will explain what is that. It's a shifted version of the commutative structure sheaf. Yeah, let me explain what is that. And yeah, first of all, look at this, our topological space, CXY, so union of two lines, two complex lines. On the left, we have standard sheaf. On the right, but they must be compatible at 0, right? So look, I have written here, f of z, g of w, at 0, they should equal. So all these couples, that's called exactly a fibered product. So the commutative structure sheaf itself, there's a fibered product of two structure sheaves of lines, x line and y line. Okay. Yeah, by the way, pay attention here. Every set here, they are Q open sets. That's why they both automatically contain origin 0. In every Q open set, we have 0 in. That's why it makes sense. So in some sense, this is not the same sheaf as from the standard complex analysis, because topology is different. So you should look at the direct image here. Yeah, but it's understandable, right? So it's a standard sheaf of homomorphic functions. Okay, so now I can do there sort of a shifted version. So what's the meaning of that? Let's look at the z power d principal ideals. Just multiply by z power d's. This one generates a new filtration of sub-sheaves. We can also connect them like taking the d's derivative over d factorial. So, you know, about 0, their Taylor series is gonna start from z power d, right? Z power d's. So that's why we need to take the d's derivative divided by d factorial. Anyway, so OD is again fibered product of these two sheaves, OXD, OYD. So this is our shifted version of the structure sheaf. Okay. Yeah, look, this is again compatible map. This is our projections. If D is 0, we have the original sheaf, O. Okay. We have original sheaf. Okay, now result is understandable, right? Let me turn back a bit. So what I mentioned here. So this sheaf, this is a non-commutative sheaf, is actually as a Fréchet space sheaf can be written as a direct product of all these sheaves, shifted versions of OD. So that means we can by somehow define multiplication here, which extends the multiplication of the quantum plane. The Q multiplication can be defined there. Yeah, let me say this is a non-trivial result. I mean, it's not so easy to understand what's going on here, where did it come from, all this stuff. Okay, this sort of decomposition result, or sometimes the quantization result, how to get our structure sheaf. Okay, now, you know what's been Runge open set, right, from the complex analysis. So open set is right, it has no holes, or every component is a simply connected domain. So ring open set, it's a set when polynomials, we have density result, right? Polynomials should be dense here, right? Okay, it's Q version, Q open, Runge open set. It's called Runge Q open set, right? Well, actually, the basic Q open sets, all of them, they are Runge Q open sets. We have actual topology base in Q topology of Runge Q open subsets. Well, how they construct, that's easy. Look, just briefly explain. For example, let's take any point on the complex plane and some Q neighborhood. So, you know, the Q neighborhood, it contains zero and it's stable under Q action. So the Q hall of lambda, if you multiply powers to Q lambda, all of them will be inside of U. But since U contains the origin, it contains small disk. So outside of the disk, you can find only finite number of them, find many of them, and you can cover them up again with special disks and unify them. Look, this is going to be a Runge Q open neighborhood of lambda. So this is just topology base. We have enough of all of them, Runge Q open sets. Okay, for union of two lines, for our spectrum, CXY, we say they again Runge Q open set if both components, they are Runge Q open subsets. Oh, look, the same Q version of the density result. So if you have a Q open subset, then U is a Runge Q open subset if and only if quantum plane should be dense here. So here we have if and only if. So this is a nice set, right? Again, with the same nice property of density, but now in the non-commutative algebra, FQU. Okay, so the final attack, what about this resolution for our FQ? So I will skip the notation U. Again, what we are doing here, the essential moment, I'm using again the same decomposition theorem in terms of this shifted versions of the structure, commutative structure sheaf. So if you're tensoring them using the property of the direct product and projective tensor product, I can write down my second tensor problem like that. Look, this annotation ODL for this projective tensor product. So, but be aware, this stuff as a Fréchet space is quite complicated. Imagine here we have two variables here, and overall we have actually four variables. So, but all of them by somehow compatible because every one stands for the crossing space, union of two lines. So union of two lines here, union of two lines here. So as a result, this one is a sort of special Fréchet space of quadruples. So this is a technical side. It's so complicated here to deal with this one. Anyway, so we can write down the same complex. Look, the same complex RFQ. And we can introduce a special order here just to pick up homogeneous by homogeneous terms when D plus L is N, for example, like that. Anyway, we have a special order here, special order here. So look, this is our complex. So concerning differentials, again, some of them, I mean, D0, D1, they have a lower triangular shapes. Look at the diagonal. Diagonal, they are special, like commutative multiplication operators, but they're acting on the quadruples. Again, they have a special action here. Lower diagonal, we have differential operators. They're special differential operators and difference operators. So D0, D1, they have nice lower triangular shapes. But pi has no diagonal shape. So that's the main problem here. So pi generates a serious problem for us. Okay. Yeah, look at the diagonal. Again, we have diagonal complex here, right? Diagonal looks smart. Look at this. Special multiplication operators. Pi dl. Pi dl is acting like that. I told you we have 4 variables. Look. And if you calculate the homology groups, so look, 0, we have fluctuation here, OU. Second is 0, third is 0. So we have a problem here. But this one is not affecting seriousness. So at least diagonal is not exact. Yeah, nonetheless, we can prove the main result. This technical is really complicated. It's challenging. Lots of calculations here. So if U is a Runge Q-open subset, then is a localization. So actually, that complex, I mean, is a resolution. But we cannot prove it as a split. We don't know whether it's an absolute localization or not. But what we do know is just a localization. Well, also every Q-open subset is FQ acyclic. This another result, actually that question raised by Alexei Pirkovsky in our, I don't know when, maybe in one of my previous talks. So problem solved here as well, but I don't like to talk about this result right now, maybe later. Anyway, we have all these nice properties here for this structure sheaf. Okay. Well, just finally, I would like to say a few words about the spectra. So first, conclusion, what's happening with the Taylor spectrum and another spectrum, so-called Putinar spectrum. So you know what is the Taylor spectrum? Again, so suppose we have a left Fréchet module given by a couple of operators, continuous linear operators with this sort of relation. So we say just as a left Fréchet Q module. So we can define the resolvent set as a set of those characters. We have this transversality property. This is a one-dimensional module generated by gamma. So it should have behavior, the transversality behavior with respect to X. So look, that's the meaning of that. The complement to this resolvent set inside of the character space, that's called the Taylor spectrum of this couple, T and S. Yeah, by the way, if Q is 1, absolute values can be empty, just it's not surprising. If Q is 1, it's quite different theory here. So that's why let's assume Q is less than 1. Okay, now we have a nice sheaf, structure sheaf. We can also define resolvent set of the sheaf with respect to X. Now we pick up those characters, which has some Q-open neighborhood, but with this sort of transversality property for every Q-open subset. Yeah, we know the structure mainly in the commutative case developed by Mikhail Putinar. So that's why we follow him up in this manner. But now we have a non-commutative sheaf. So this set is Q open subset. By the way, concerning the previous one, this set we don't know whether it's open or not. Actually, it may not be open. So complement to this set, that's called Putinar spectrum, but now it's definitely closed, I mean Q closed. So this is a Q closed set. Okay. Okay, look, that's a result. So if X is a left Fréchet Q module, then Putinar spectrum contains the Q closure of the Taylor spectrum. But if X is a Banach left module, then we have this equality. So the Putinar spectrum turns out to be the closure, Q closure of the Taylor spectrum. Well, but what about concrete example? So for example, can we compute it directly? Yeah, look at this example. Let's look at the standard example in LP space. So we have a shift operator and diagonal Q operator, S. Look, this S, T is shift, S is diagonal, Q diagonal. So if Q less than 1, S is a compact operator with the spectrum, which is Q hollow of 1. But for T is a unit closed disk. Okay, and certainly we have this relation. So this couple T and S generates a Q module, left Banach Q module. First of all, we can compute the Taylor spectrum directly, precisely. Taylor spectrum looks like that. Yeah, I had a talk about the spectrum. I proved it some inclusion here, but now I can say that the precise equality here. Well, we need to involve some index theory of Fredholm complexes and use it compact perturbations. The pay attention, S is a compact operator. So that's why we can involve this theory here, mainly developed by Feinstein and Victor Schulman. So if you involve this theory, you can prove that actually we have the equality here. So what is that geometrically? On the left-hand side, we have a ring annulus within 1 and Q minus 1. So we have a ring here about 0. On the right-hand side, we have just single point 1. So you got this is a Taylor spectrum. So what about Putinar spectrum will be its closure. But I told you the topology is so weak here. So you need to take the closures of both sides. If you take the closure of this ring, you will end up with the complement of the unit open disk. So just quite huge. All complex plane apart from the disk. Another side, right-hand side, will be spiraling, but in opposite direction toward infinity. So it's rolling here toward infinity. So as a result, we got quite a big set. Look, so we have a huge gap between Taylor spectrum and Putinar spectrum. By the way, in the commutative theory, they are the same. We have equality here. But here we have a huge gap. Okay. Yeah, so concluding remark, as I told you, so Taylor spectrum, could have quite a large Q closure, which results in the Putinar spectrum. By the way, we're expecting functional calculus, holomorphic functional calculus about the Putinar spectrum. So that's why still I don't know this result precisely, but I have a suspicion that the result will be true. But for for special sets, quite big sets. That's, I mean, I don't know why it's so happening. Probably the out of Q, the Q generates something like that. Yeah, and we shouldn't expect spectral mapping property. Look, this is quite a, I mean, the news here, so as we can see, comparison to the previous theory. For example, in the representations of the nilpotent Lie algebra of operators. So we have a huge difference. Even we are not expecting to have some normal spectral mapping property. So the functional calculus and spectral mapping, they should be quite different. And they're quite a different specifics. And Taylor spectrum behaves really bad comparison to hard spectrum. So this one exactly tells you, so this stuff like Taylor spectrum, Putinar specially designed for functional calculus problem, not for spectral mapping property. Anyway, so we have a series gap mainly caused by this weak Q topology. Yeah, probably it's also interesting stuff here. Okay, yeah, that's all. Yeah, thanks for thanks for your patience. Okay.
Thank you very
Thank
much.
you.
Thank you. Are there any questions, please? Or remarks?
Critics, please.
Well, I have a question
Sure.
about probably related to last slide. So we see that the Taylor spectrum is not the same as the Putinar spectrum in the non-commutative case.
Yeah.
I was wondering how about the hard spectrum? How is it related to Taylor's and Putinar's spectrum in this case?
Yes, yeah. Well, concerning hard spectrum, I mean, hard spectrum behaves well. So even we can prove some projection property, even spectral mapping theorem for hard spectrum. Well, probably hard spectrum designed for that, so for spectral mapping property. But how does it relate to Taylor? Certainly is bigger than Taylor, but I don't have concrete example. I need to calculate the hard spectrum. Well, I have somewhere in my papers. So, but certainly they have no direct link, right, with each other. The Taylor spectrum is quite very homological, it's quite different. It comes out, well, topological homology is some property. But hard spectrum is a very sort of algebraic, I mean, very operator stuff. Yes, for hard spectrum is okay. By the way, Hart himself proved that spectral mapping, non-commutative spectral mapping property, polynomial for hard spectrum, that's true. So that's why this is quite nice in this manner. But the problem in this theory tells us like we should separate them seriously. They are quite different stuff. But concerning the precise, for example, for this example, yeah, I don't know precisely, but probably we can calculate both of them and we can see what's the difference there.
Mm.
I think we can do like that. Yeah, thanks for this question. This is
Thank
crucial,
you.
exactly that I was trying to explain. So look, so don't expect spectral mapping property here. So Taylor spectrum, there's a quite different stuff.
Mm.
So look, that was also out of my expectation in this Q theory. I thought that the Q theory should be something easier to deal, but it turns out it generates a serious problems. I don't know why, so why so happening.
Mm. Yeah, I see.
Mhm.
Well, another question is, what if we have more than two variables? Uh, can we prove
Oh,
something?
yes. Yeah, good question. So maybe someone else. If someone wants to commit the suicide, yes, please. So I told you here, we have four variables here in the calculations of the bimodal resolution, the quadruples. Look here.
Mm-hmm.
This stuff, there were quadruples here, four variables. So if you get more variable, probably I don't know how many variables there will be. So but it's a special work. Someone needs to deal with to do all these calculations precisely. But my suspicion it should be very challenging stuff. I don't know. Maybe someone else could find easy way how to simplify all these calculations. But as far as I can see, what I got here is this really challenging, technical hard. I don't know. Yeah. Yeah, someone else, please.
Okay, thank you. Okay, more questions, please. Well, if there are no more questions, then let's thank the speaker again. Thank you very much.
Yeah, thank you.
Okay. Okay, so see you next Friday. Next Friday, our speaker will be Vladimir Markovich Manuilov. So we are looking forward to listen to have his talk next Friday.
Okay. Yeah, thank you.
До свидания.
Ну, всего доброго.
До свидания
Всего
всем.
доброго.
До свидания.
Bye.
Goodbye.
Bye.